Welcome to the video on circular motion. In this video we're going to discuss what is called centripetal motion, how it's different from centrifugal force or motion. And we're going to look at the equations and all aspects of circular motion and the causes of circular motion. Let's start with some demonstrations. Take a look at this.
I got here some water. I got some water here, gang. I got the water in the bucket. You guys know what I'm going to be doing with the water in the bucket? Because we're talking about centrifugal force, aren't we, right? I'm going to take this water in the bucket. What am I going to do? I go right over my head, and when I get to the head top, I'm going to stop, right? No, I ain't going to stop. Okay. Not if I can help it. I just don't. Okay, maybe toward you guys, huh? Okay. You have confidence in the laws of physics, huh? But this is water, gang. Okay. How come the water didn't fall out? How many say, well, there's probably no reason for that. It's just that when it's spinning, the laws of physics break down. How come the water didn't fall out? Why? I take the ball on the string, and I swing the ball around and around and around. Or I swing it around like this. Okay? Or like that. How come the ball goes in a circular path? Maybe because something is pulling the ball out. That's what the little kids say. But you guys say, wait a minute, there's nothing pulling the ball out. Which way is that ball being pulled, gang? In or out? Begin with an I. Now try it. Okay. That's being pulled in. You know, a lot of people don't know that? They think that something's pulling the ball out. They think that when I whirl the water around and around and around, that something's pulling the water out. And they have a name for that. You know what they call that? They call it centripetal force, center fleeing force, a force going away from the center. But guess what, gang? There is no centrifugal force pulling outward on this ball, and there was no centrifugal force pulling outward on that water. The forces that acted on both these things was pull which way? Inward. I have to pull on that string. If I stop pulling and let go, what's going to happen? The ball going to go out? Or just continue going? And this is the law of inertia.
Or how about this one?
Take a look at this. You're just going to use a clear balloon. So you're going to go to the store and you're just going to buy a clear balloon. Okay. And in that clear balloon, you're going to put a penny. So I already put one together for you, so this one will be yours. Okay. So the penny goes into the balloon like this, and now you blow it up. So remember when you went to the circus as a kid, that guy on the motorcycle? Yeah. And he would go in that cage and kind of go round and round. Centripetal force, not centrifugal, but centripetal. So watch this. You're going to hang on to it and shake it up a little bit and then spin. And as you spin like this, you get this beautiful spinning penny sitting inside. Isn't that just gorgeous?
Oh, that's so cool.
It just goes around and around and around. It's kind of like those planets going around that sun and the moon going around the Earth. That satellite that's in geosynchronous orbit that's sitting there just around and around and around. And now notice that if we were doing this on the space shuttle, the difference between what the kids would see down here in the space shuttle is that up in space that would just keep going and going and going, but of course the effects of gravity continue to pull it down. Now, this is a nice quiet activity, and most teachers like quiet activity at the end of the year, but you don't. So here's what I want you to do. This is the perfect thing. This is a hex nut. So you find a hex nut, and you drop it down inside here. Imagine a room. I just came back from El Centro, California. Yeah. In a room of 100 teachers all doing this at the same time. Spin that one and listen to that one.
Oh, my finger got it.
This is a screaming penny, which is just beautiful. So now we get vibration. This is a librarian's worst nightmare, right? Hey kids, let's go and examine science a little bit. Isn't that fun? Centripetal force. But you know the one that everybody wants to see you do, of course, is this. And so here is the device that, of course, you're just going to want to make it home. Because why would you want a spoon if you're going to stir up your liquid?
Right.
You need this tray, all right?
Of
So
course.
the tray goes like this. Is that kind of nice? And now to that tray, we put a glass of water, which is nice. So a glass of water goes here. And you could just do one, but you are going to have a dinner party. So we need to have a lot of these, all right? So here we go.
Oh, I
A little
love the dinner
centripetal
parties.
force, we would only hope that it would just stay in place, okay? So I think you're going to be just fine. And if not, gosh, was it fun seeing a meteorologist spin this
And
over?
I'm wearing white today. I'm so
Okay, you're
glad
gonna
I
be
heard
great.
about
All right,
this
you feeling
experiment
good?
before.
All right, good. So now
Okay.
here's what I want you to do.
Yeah.
You're going to get a little just kind of rocking action. That centripetal force, it's a center-seeking force. Ready? Kind of up and over your head. 1, 2, 3, up and over your head. Here we go.
Oh.
Nice. See, you did it. You did it. Go again. Come on. Be brave. Be brave. Nice.
There we go.
Nice. Nice. It's okay. It's okay. You're just like $100,000 million cameras, but you're fine. At least the dinner party had one left. You get crazy there for a second. You were done.
Lastly, how about this one?
Hello, I'm Jeff Williams on board the International Space Station, Expedition 22, and today I would like to talk to you about centripetal force. If you were to take a liquid and you had bubbles in the liquid, what would happen to the bubbles? They would rise up, right? Well, here in space and weightlessness, I have this bag of tea, and you can see it has bubbles in it, but they don't rise to the top. In fact, I'll shake them up here, and you can see the bubbles spread out throughout the tea. The bubbles don't rise to the top in the absence of gravity in this weightless environment of the space station. But if I were to rotate this, and let's see if I can rotate it and keep it in your view of the camera. Let's watch what happens. If you look really close, you'll see the air bubbles starting to coalesce in the center of the tea bag. In fact, let's see, when I bump it, they move. I'm trying to get it in your view here. There it is in your view. They make a perfect circle, unless I disturb it. Let me try that again. See the air coalesce to the center, form a circle. Due to the centripetal force applied in this, because it's turning, it's rotating, the liquid goes to the ends and the air ends up in the center of the liquid. Very interesting. As soon as I stop, you can see the liquid disperses throughout.
So circular motion is one of the most difficult topics for students to grasp onto, because all that you study and you learn in the textbooks indicates that centripetal motion, centripetal force resulting from centripetal acceleration is directed towards the center of the circular path. And the problem is that that's not what the person feels when they travel in a circular path. Let's take this consideration where we have a circle, and this is your path traveling in a circle as viewed from above. This could be anything. Probably the most common example you'll relate to is traveling through a left turn while you're sitting in a car. Okay? You certainly don't feel pulled towards the center. What you feel is your body leans outward to the right, so you feel that as a pull. We'll talk more about that later. Okay? The reality is here that what's happening is as you travel around that circle, that your velocity is tangent to the circle at any moment. So what we're going to do is we're going to take and draw some velocity vectors at each of these key points here along the way. And we'll go ahead and label them here in a moment. What you see that any moment or instant in time, your velocity is tangent to the circle. So what's happening at each of these spots is that your body wants to stay straight. However, the vehicle that you're in is turning to the left. That's why you feel a pull to the right, even though that's not a force that you feel. That force, by the way, is, as you heard in a previous video, is called centrifugal force, outward-seeking force, and there is no such thing. Okay? So the question becomes, what is it that keeps you traveling in the circle then if there's not an outward pull on your body? Well, let's take this moment let's take this instant right here. Okay? And what you experience is a centripetal acceleration which results in a centripetal force keeping you towards the center. Okay? Let's look at the equations first, and then we'll talk about the causes of this here in a moment. This is going to look very familiar to you because in our unit on Newton's laws, we said sigma F equals ma. And after writing this statement, we always asked ourselves, is the object, is that mass accelerating? And we would say yes or no and then proceed with the problem from there. Well, when an object travels in a circular path, the answer is yes. The object is centripetally accelerating. So, that means as a result, Newton's second law, if an object is accelerating, there's a force on that object directly proportional to that acceleration. Well, that acceleration is calculated by the speed of the object squared divided by the radius of the circular path. Okay? So these are the equations that we're going to be dealing with in our circular motion unit. However, there is a very key point that we need to get out of the way here. And that is that Fc is always caused by another force. When we label a free body diagram in circular motion, we never put Fc as a force on our free body diagram. And that is because the centripetal force is always caused by some other force, or a combination of forces actually. So let's go back to our sample example here. What is it that keeps you traveling in a circular path as your car turns to the left? Well, if you think hard about it, what keeps you traveling in a circular path is the static friction between you and the seat. Static friction is a cause of centripetal force. What are some others? Gravity can keep an object traveling in a circular path. Great example of this is the moon traveling around the earth, or the earth traveling around the sun. Or how about any of the satellites that we put in orbit around the earth, the communication satellites, the International Space Station you saw in the video, etc. What about in Paul Hewitt's demonstration with the ball on the end of a string? What's keeping the ball traveling in the circular path? Well, that force is tension. The tension in the string is keeping the ball traveling in the circular path. What was it keeping the water in the bucket traveling in a circular path? That force was the normal force between the water and the bottom of the bucket and the walls of the bucket itself. Okay? So here are some causes of centripetal force, and you can actually, in some cases, have multiple interactions between these forces. Say if you have the bucket traveling in a vertical circle, you actually have the weight down in the normal force either up or down depending on whether the bucket's in the top of the path or the bottom of the path. So there you have it. There's your discussion on circular motion, centripetal force resulting from centripetal acceleration.